Hello everyone, welcome to lecture number 6. So today we will continue the Michaelis-Menten equation, and we will look that how the Michaelis-Menten equation, as you can remember that we have derived this equation in the last lecture. So the enzyme catalysis follows this reaction scheme where the rate of the catalysis is also denoted by the velocity of the catalysis, or we can simply call it the speed of the reaction, and sometimes it is denoted as V cat, is equal to the rate finally depends on K3 multiplied by the concentration of ES, and we have found that this expression came down into something like that, which is denoted as the Michaelis-Menten equation after the uh, uh, the two famous scientists, Michaelis and Menten, who initially derived this equation. So we have a constant here, as I also mentioned last time, that this is called the Michaelis-Menten, or this is called the Michaelis constant, Km. And so in this lecture, first we will look how this equation can be graphically represented and what is the interpretation of the Michaelis constant Km, and a few more important aspects of this enzyme kinetics. Okay, so let's start. If you look at the equation over here, so we can interpret that at low substrate concentration, when the substrate is, we can say that it is so low that it can be negligible with respect to the Michaelis constant, whatever may be its value. So then it implies that the velocity is something like some constant multiplied by the substrate concentration, because if we neglect that, everything becomes constant except the substrate concentration. So this is nothing but basically a first order reaction, or first order kinetics. And in other words, at very high, on the other hand, if the substrate concentration is very high, so that the Michaelis constant can be neglected from the denominator, then you see the velocity, because this is neglected, so S cancels out on both sides, means in numerator and denominator. So velocity becomes something constant, because here K3 is a constant and E naught, the initial concentration of enzyme, is also a constant. So therefore the enzyme follows a zero order, this enzyme catalysis follows a zero order kinetics. Okay, so how to represent this graphically? So let's try to plot it by putting substrate in the x-axis and velocity in the y-axis. So if we do so, you see so the substrate concentration can start from 0. So at lower value of the substrate, the V versus S curve is just like an equation of a straight line passing through origin, right? Y equal to mx. So we would get the data points initially something like that. So that means it would give me something of a straight line. The best way gives us a straight line, and then at a higher value of the substrate, you see the velocity is independent of the substrate concentration. So that means we should expect some points, the best fit of which should give us a straight line parallel to x-axis. So if we neglect the actual data points, and if we just try to draw the trend, or in other words, the best fit of V versus S plot, the plot looks something like this. Okay. Now you see at a higher concentration of S, okay, the velocity finally gets maximized and constant. So this velocity over here we denote as V subscript max. So V max means the maximum velocity the enzyme catalysis at all can achieve. And so you see at lower concentration of S, velocity increases with the substrate concentration, but after some point, the velocity gets constant. So in other words, we can take this as if the velocity has got saturated. That means the rate of the reaction is not increasing anymore. So Vmax is also called the saturation velocity. All right. So this is how the V versus S curve looks like. So now from this plot, we will try to get a physical interpretation of the Michaelis constant Km. Okay. So what about this? Now if we look at this equation, and from this equation, if anyone puts S is equal to Km, so right here we can write if we plot V is equal to K3 E naught divided by S multiplied by S divided by S plus it's okay here. Okay, so what I have put that putting S is equal to Km. Okay, here. So if I exactly replace the value of Michaelis constant with the constant substrate concentration S, we get an equation like this, and which gets reduces to. So now let's take a look at that. What is Vmax? So Vmax is nothing but K3 E naught. So I'm going to replace this K3 E naught as Vmax over here in this equation. So we get V is equal to Vmax S multiplied by S divided by 2S, and the S at the top and S at the bottom cancel each other out, and we finally get something of value Vmax divided by 2. So from the graph or from the equation, first we see that the velocity becomes exactly half of the maximum velocity. So this maximum velocity is Vmax, and somewhere exactly half of that means half of this value. So it gets somewhere here. Okay, so I'm drawing the line approximately. So this is the value of Vmax by 2. So now the equation tells me that we reach the Vmax by 2 value whenever the substrate concentration becomes numerically equal to the Michaelis constant. Okay, so then from here we can try to get a formal definition of the Michaelis constant Km. So the Michaelis constant, now we can write that Km is the substrate concentration at which the velocity of the catalysis becomes Vmax divided by 2. Okay, so from the graph plot in the backward, if we do the backward thing, that is whenever, so we will try to find the substrate concentration at which the Vmax becomes Vmax by 2. So V by S plot, V versus S plot gets Vmax by 2 at this point. So I'm going to draw a line to find out the substrate concentration at which it happens. So this value over here, whatever the substrate concentration, so this particular substrate concentration is actually the value of the Michaelis constant, that is Km. Okay, So from this graph plot, one thing is very clear, that if I have a lower km value, so that means the velocity would reach the maximum velocity faster. Or I'm sorry, that's not the correct statement. The correct statement is that if I have a lower km value, so the velocity would reach the maximum velocity at a lower substrate concentration. Okay, so you can verify it out from here that if I have a lower km, for example, the km value is here. So if I have a lower km, then my km value is over here. So that means that and if I want to draw the graph over here, so we have to draw the graph something like this. Yes, so this is my new km, and I can call it km prime. So you see, at this situation, so I have a new kinetics where I have a lower km value, so that means my enzyme is reaching the maximum velocity at a lower substrate concentration over here. So it was reaching at a higher concentration in the previous case. So now it is reaching the maximum velocity at a lower substrate concentration, which is here. So previously it used to be here. So therefore, in other words, if I have a higher Km value, so the enzyme would take more substrate concentration to reach the maximum velocity, or Vmax. Okay, so from this discussion we can try to get an idea of the Michaelis constant, okay, and its physical interpretation. So now one very important point is that this Km, or Michaelis constant, is specific to particular enzyme catalysis, because if you look at the original definition of Km, you see that Km is dependent only on K1, K2 and K3, and those K1, K2, K3 values only depend on that particular enzyme and substrate and the active site and the enzyme substrate complex. So that means it is very much dependent and specific to the enzyme substrate pair. Okay, so that is the number one salient feature of the Km. In other words, we can say that for every enzyme catalysis, the constant Km value signifies something special about the property of the enzyme or the concerned enzyme catalysis. And the second point is that Km is a measure of the enzyme's substrate affinity. So I believe that it would be better if I write that statement over here, that Km signifies, or Km is a measure of the enzyme's affinity for the substrate. So that means of course that when we say that at a lower substrate concentration, the enzyme is performing at its best value, that means Vmax. So that means we can tell that the enzyme has the higher affinity towards the substrate. And also the another name for the Km is called the half saturation constant. So if you come across this term somewhere in any textbook or any other context of enzyme catalysis, so please do remember that this term half saturation constant is referring nothing but the Michaelis constant, or the Km. So before we finish this particular graph plot of V versus S, a question to you that in enzyme catalysis, okay, which enzyme performs better with a is it an enzyme with a higher Km value or an enzyme with a lower Km value? Okay, so this is something. Uh, this is some question that we have to really think well before we go to answer this. So what we do now, that we will now next move on to few other parameters to see from which angle it is best to comment on an enzyme's efficiency. So that means which enzyme is working better and which is not. So how to answer that question. Okay, and from that we will introduce ourselves to another kind of graph plot related to this Michaelis-Menten equation. Okay, so let me clean the board and start the discussion right away. Okay, so let's begin with the debate that whether Km signifies an enzyme's efficiency. So to tell you directly that Km signifies enzyme substrate affinity, definitely for sure, but a caution should be taken that the Km Michaelis constant does not measure an enzyme's efficiency. Okay, so before that, let us also remember that the Michaelis constant and Vmax, as the maximum velocity, are independent of each other, so they are not related. And we cannot predict Vmax from Km or vice versa. Okay. So now let's look at the Vmax. So Vmax means it is the rate, the maximum rate at which the catalysis would be done. So basically, this is the outcome of the catalysis. So higher the Vmax, so that means like the more number of the molecules per unit time would be getting converted into the product. And we want that number to be high, isn't it? So that's the goal of the catalysis. So whenever we are talking about the catalytic how good the catalyst is, so we will always be talking about some number, and if you look at that, so Vmax is equal to K3 E naught, and E naught is the initial enzyme concentration. Okay, so if we keep that fixed, then the Vmax is a function of K3, and so K3, you remember that it is the final conversion step where the enzyme substrate complex breaks down into product plus the enzyme back. So the K3, the rate constant, that actually governs the product forming rate. So what we can tell that this K3 is a very important parameter for enzyme catalysis. And this K3 has another name. So the K3 is also known as the K cap because that is actually the catalytic rate constant, because we see the final conversion over here. And this is also known as turnover number. And you see K3 is a first order rate constant and its unit, so the unit of the turnover number, also called TON, is second inverse, okay, or time inverse. So we can write time inverse. So it's a number, numeric value. And higher, we want an enzyme to have a very high turnover number. So that means it would convert a very high number of molecules into product per unit time. So now here comes to the point, efficiency. So is the turnover number itself directly talks about the efficiency, or isn't it like in the last in the last few minutes, means the one that we have discussed just previously, I told you that an enzyme, if it has a lower Km value, it would require a lower substrate concentration to show its maximum velocity. And the maximum velocity is actually K3 if E naught is constant. So ideally what we want? So ideally we would want that our best enzyme should be reaching to the maximum velocity with a very little substrate concentration, and that maximum velocity should be very high. So therefore we have a new parameter we call, this is enzymes efficiency. Okay, so this is denoted by a ratio. Okay, so this ratio is called, it's a ratio of the turnover number K3 divided by the respective Michaelis constant, that is the Km. All right, so that means if we have a lower Km and higher K3 value, so that we would be reaching an ideal situation where the enzyme would require a very low substrate concentration to reach its maximum performance point, and that point is also very high because we have K3. So therefore this ratio denotes the enzyme's efficiency. So remember this small little numerical value means this formula, basically K3 divided by Ka. And in real life, biological enzyme have higher turnover number, and sometimes easily the turnover number reaches 1,000,000. For example, there is an enzyme called carbonic anhydrase which has a turnover number something close to 10 to the power 5. Okay. So the thing is, next question is that how to determine this turnover number, or in other words, how to determine the K3. Because if we want to know which enzyme is working best and which is the most efficient enzyme from a group of enzymes, we have to know K3, because the K3 is related to Vmax. So once again, so how to know K3? Of course, if we know the Vmax, and Vmax can be known from the graphical plot. So from that Vmax, E naught is in our hand, we already know it's a literature value. And from the Vmax, we can definitely know K3. But the question is how to know Vmax in a most sensible way. Alright, so I'm going to clean the board and I will start with the graphical presentations from where we would be able to know Vmax easily. So the question is how to know the Vmax. So if we try to plot the Michaelis-Menten equation directly like this by putting V versus S graph plot, definitely we have to deal with a non-linear equation. Means this is a definitely not an equation of a straight line, so it's a curved line there and then it flattens out. Now in those earlier days where computer software based help was not there, so people used to find it very difficult to plot or to make the best fit for a non-linear graph plot. So at that time it was much easier to find the best fit for a straight line. So what actually was done, that two scientists and their name was one of them was Lineweaver and another person was known as Burk. Okay, so these Lineweaver and Burk, they introduced a new form of the Michaelis-Menten equation in order to obtain a much easier graph plot. So what they have done, they have taken the reciprocal of this Michaelis-Menten equation. So 1 over V is equal to, if we take the reciprocal, this becomes S divided by V max multiplied by S plus Km divided by V max multiplied by S. So here also S at the top and S at the bottom, they cancel out, or we can get 1 over V is equal to 1 over V max plus once again we have Km divided by V max multiplied by 1 over S. And you see that this equation is in the form of straight line. So this is y is equal to c plus mx. So this is the slope. If we plot 1 over s in the x-axis and 1 over v in the y-axis, and we get 1 over v max at the intercept in the y-axis. So therefore, if someone tries to graphically plot that by taking 1 over s at the x-axis as the independent axis, and on the dependent axis if we have 1 over v, so definitely the observed data actually comes something like this, and it is much easier to draw a best fit straight line. So by drawing a best fit straight line of those obtained data points of 1 over v versus 1 over s plot, we get a straight line. So from the slope we can easily calculate this value Km divided by V max, and the intercept over here we know already that this is 1 over V max. So from the graph plot, if we can calculate the intercept on y-axis and the slope as well, so from that we can easily calculate two things. That is, of course, we can calculate Km, and if we take the inverse of the slope on the y-axis, we get the V max. So due to these two people, Lineweaver and Burk, this kind of graph plot is known as Lineweaver Burk plot. And in enzyme catalysis, you will see these Lineweaver Burk plots are frequently appearing. So from now onwards, we will make ourselves familiar with this kind of Lineweaver Burk plot. And there is also another name of this Lineweaver Burk plot that is called the double reciprocal plot, because we have taken the reciprocal. Okay, so we have 1 over v versus 1 over s. So it's the reciprocal of the velocity versus reciprocal of the substrate concentration. So two reciprocals. Due to these two reciprocals, this kind of graph plot is also known as the double reciprocal plot, or the Lineweaver Bar Plot. So once again, this board over here looks a bit clumsy. So I am cleaning the board, and let's try to make a nicer representation of the double reciprocal plot. So 1 over s versus 1 over v. And then we have the straight line perhaps appearing like this. And we know the slope is Km over V max, and the intercept is 1 over V max. So the question is, what is the intercept of this line on 1 over S axis? Okay. So that means we have to extrapolate this straight line. So if we extrapolate the straight line, definitely we reach here, okay, a point. So the question is, what is the value of this point? Okay, So can you calculate that? Well, the answer lies in the double reciprocal equation, the Lineweaver Burk equation itself. So this equation, 1 over V is equal to 1 over V max plus Km divided by V max multiplied by 1 over S is also known as the double, the Lineweaver Burk equation. So the question is, what is the value of 1 over S when 1 over V becomes 0? Okay, so that is the point telling me. So from here we easily put 1 over V is equal to 0 is equal to 1 over V max plus Km divided by V max multiplied by 1 over S. So therefore from here we get that 1 over S is equal to, if we keep that over here, so it would be okay, so let's write few steps, doesn't matter. So minus 1 over V max is equal to Km divided by V max multiplied by 1 over S. So V max and V max cancel out, so we have minus 1 is equal to Km divided by S, and or we have 1 over S, we have 1 over S is equal to minus 1 over Km. Alright, so now we get a value over here. So this point is minus 1 over Km. So this is also defined, this point is, this is the value, this is the point where 1 over V becomes 0, and the value of 1 over S becomes minus 1 over Km. Okay, so the question for you, that if we have a higher Km value, so how would the graph plot look like? Means I have another like we have another straight line to draw, and the condition is, for that straight line we have a higher Km value. So you see the slope is Km by Vmax, and I am also considering that the Vmax is same, only the Km gets increased. So can you draw that from here? So you please try to do that. So Vmax m means the intercept is same, but we have a higher Km value. So means how would it look like? So that means the slope is higher. So the slope is higher means the curve would look like something like this, isn't it? So higher Km value means we have lower minus 1 over Km value. Okay, so does that make sense? Anyway, it's for you to figure it out. So now, as we have familiarized ourselves about the Lineweaver Burk equation and Lineweaver Bar Plot, we are going to move into a newer topic, and the topic is called the enzyme inhibition. So let's explain that. So here we start a new topic. It's called enzyme inhibition. So from this point, we would concentrate on the topics of enzyme inhibitions and different types of inhibitor, and also different types of inhibition kinetics. So what is an inhibitor? So inhibitor are typically certain biomolecules. So the biomolecules that actually inhibit, or it actually puts some constraints on the enzyme so that the enzyme is unable to work with its full efficiency. So typically the substances that actually slows down, okay, or sometimes it halts the action of the enzyme, we call those agents or biomolecules as enzyme inhibitors. So now you might be probably wondering that why we are talking about this enzyme inhibitor, why at all we are interested in the kinetics of enzyme inhibition. The sole reason is that these enzyme inhibitors are actually give us a major option or a major way to find out the different metabolic pathways of organisms. So we can write that it helps, it means the studying of enzyme inhibition, it helps us to understand uh, the various metabolic pathways in the organism. So probably you have heard about different metabolic processes in living organisms. For example, the formation of ATP. Okay, ATP is also known as the energy currency. So how ATP is formed and how from the ATP we get the energies back. And so those are the part of a metabolic process. So and how to know the exact mechanism of those metabolic processes. So those enzyme inhibitors actually helped us a great deal to understand those metabolic pathways. So that's why it is very important to know a little bit detail about the enzyme inhibition. So we will first start with the different types of enzyme inhibitors. Okay, so there are two kinds of enzyme inhibitors, or we can classify them into two major categories. So one category is called reversible, and another category is known as irreversible inhibitors. Okay. So what is the reversible and what is the irreversible inhibitors? So the irreversible inhibitors, basically it destroys the enzyme. Okay, means you won't get back the enzyme anymore, and the enzyme kinetics is no good, and you won't get any product. So basically everything is destroyed. And of course, the reversible inhibitors is just the opposite of the irreversible inhibition. So here, it actually temporarily hinder the enzyme action, or temporarily blocks the enzyme action. So that means it actually slows down the enzyme, or it blocks, prevents the enzyme to perform at its level best. And once the inhibitor is taken away, the enzyme gets back to its actual action. So that's why it is known as the reversible inhibitors. Now there are three kinds of reversible inhibitors. Okay, so 1, 2, and 3. So the first type of reversible inhibitor that we are going to study is called competitive inhibitor. Okay, and there are other two types of major inhibitions, and there is some special case also, but exactly at this time point I'm not going to go into the details of the other classifications, but we are going to touch upon these individual categories because these are all important. These give us all important mechanistic pathways. But in today's lecture, we will concentrate on the competitive inhibitor or the process of competitive inhibition. So let me clean the board and we'll start the topic afresh. Okay, so in competitive inhibition is defined as that when in the active site other than the substrate, the inhibitor also competes with the substrate to get some complex. So the scheme is written over here. The enzyme, when binds to the substrate, forms the enzyme substrate complex and it breaks down to the product. But at the same time, it competes with another substance that is called inhibitor itself, I. It forms reversibly a complex called the enzyme inhibitor complex. Once the EI is formed, no product can be found. So here I would like to say that during the differentiation of the reversible and irreversible inhibitors, probably one point I didn't mention here, I want to mention once again that the irreversible inhibitor, the product never forms. But in the reversible inhibition, the products do form, but in some kind of hindered manner. So here, this is the example that in a competitive inhibitor, the product is being formed, but alongside there is some other activities are going on, which may actually can slow down the product formation. That we will take a look later. But for the time being, we can make a cartoon diagram of the active site. So let's try to understand, this is the enzyme and this is the active site. So the substrate can be thought about having the geometry of something like this, which can directly fit. But there is an inhibitor which may have the geometry, means the binding site geometry may be identical with that of the substrate. So here I have drawn some kind of triangular ridge here and some triangular block of S and I. But its total structure is different, but at the active site, both has the perfect match for the log. So here we are going to talk about some kind of duplicate keys. So both of them can bind to the active site, but once ES is formed, we can get the product, but when EI is formed, we don't get the product. So that's how the inhibition. So these are the rate constants K1, K2, K3 is conventional with the Michaelis-Menten mechanism as we have seen earlier. But for EI, since E and EI is reversible, so we have these two rate constants K1 prime and K2 prime for the enzyme inhibition. So now we have to find the rate law for this competitive inhibition, and that can be easily done. So remember, if we apply the steady state approximation for the only Michaelis-Menten mechanism, we get the concentration of ES something like this, concentration of E multiplied by S divided by Km. And if we apply the steady state condition on EI, that means by putting dEI dt is equal to 0, we find the concentration of EI as this, K1 prime divided by K2 prime multiplied by En multiplied by concentration of I. Okay, so therefore we will follow exactly the same route that we want to express the concentration of E in terms of E naught and S. So we have the relationship E naught. So the total enzyme concentration is now the summation of E plus the enzyme substrate concentration ES plus the enzyme inhibitor complex concentration EI. Okay, so therefore we are going to write that or E is equal to Okay, from here we can write E plus, we may replace ES by E multiplied by S divided by Km plus EI as K1 prime divided by K2 prime multiplied by E and multiplied by I. Okay, or we can take E common and we have 1 plus S divided by Km plus K1 prime divided by K2 prime multiplied by I. Okay, so therefore from here we can easily try to find the value of E. So the value of E tells me that this is E naught, this is E naught, as you can see over here, this is E naught divided by 1 plus S divided by Km plus K1 prime divided by K2 prime multiplied by the inhibitor concentration. Okay, so what we are going to do now, that now we have to find the inhibited rate. So the inhibited rate is equal to K3 multiplied by ES, and ES is actually this, and so this E can be replaced by this equation. So here we are going to write by replacing ES here. So in order to find the velocity V is equal to K3 multiplied by ES is equal to K3. Now instead of E we have this equation, okay, E naught multiplied by S divided by Km, okay, multiplied by 1 plus, I'm writing K1 prime divided by K2 prime multiplied by I. Now here I am closing the bracket plus we have Km over here and Km down there. So if we both multiply, it becomes S. Okay. So therefore, if you look at this equation, we have got the new rate equation, velocity. So the velocity, that is, this is the inhibited velocity, V is equal to K3 E naught multiplied by S divided by Km. So now you have seen, now you see we have some new terms here appearing in addition, appearing as a multiplied factor with Km, that is 1 plus K1 prime divided by K2 prime multiplied by I and plus S. So therefore the same thing or can be written as V. Now you remember K3 E naught, this is simply the Vmax. So this is Vmax is this unchanged maximal velocity divided by Km, and we denote this entire expression as some variable alpha plus S. Okay, so here we define alpha is equal to 1 plus K1 prime divided by K2 prime multiplied by E, I. So this alpha, we call it alpha a variable because alpha contains the inhibitor concentration. So that means if we change the inhibitor concentration, of course K1 prime and K2 prime will remain constant as long as we have the same inhibitor, but alpha going to increase. Or if we change the I, alpha changes, and therefore it actually changes this inhibited velocity. So here what I'm going to do now, that I'm going to write this inhibited velocity and uninhibited velocity, that is basically the Michaelis-Menten equation, side by side, and I'm going to draw a comparative analysis of uninhibited versus competitively inhibited reactions in terms of the graph plot. So let's just carry forward this equation freshly to the top of the clean board. Let's do that. So as a comparison, I have written the Michaelis-Menten equation for the uninhibited velocity versus the competitively inhibited velocity, as you can see here. Now alpha is defined as 1 plus k1 prime divided by k2 prime multiplied by I, the inhibitor concentration. So we can see that if I increases, alpha increases. And then I have written the Lineweaver Burk form of the uninhibited kinetics, and also the same for the competitively inhibited kinetics. And you see these two equations only differ here, that is in the slope. So this Km alpha is denoted as K prime, and it is also known as the apparent Km or the apparent Michaelis constant. So if alpha increases, so if we draw the graph plots with different gradually higher concentration of inhibitors, our apparent Km, that is K prime, is definitely going to increase. Now if that happens, can we draw the graph plot of the Lineweaver Burk form, that is 1 over S versus 1 over V at different or increasing concentration of I. So let's try to draw that. So first let's arbitrarily draw a straight line. This is for the uninhibited reaction. Okay. So here we call it that alpha is equal to 1. So once alpha 1 means here the Km prime, or also we can write that Km is equal to Km prime. Okay. So now next what happens if I take an arbitrarily another value, that is alpha is equal to 2. So the Km prime is actually double the Km. So you see here this is the slope. So the slope would definitely increase, or so therefore if I try to draw the new plot here, so the plot would look like this, okay, and we call it Km prime 1, okay. So for Km prime 1, we can say alpha is equal to 2. So this is completely arbitrary, so this is not exactly to the scale, so this is just kind of an indicative representation. So therefore if I extend or extrapolate, we'll have an intercept over here. So this would be minus 1 over Km prime 1, and this is earlier, that is minus 1 over Km. Okay. So now I am going to draw the graph for alpha is equal to 3, that is even with a higher slope or higher apparent Km. So the higher apparent Km may look something like this, and we can call it Km prime 2. Okay, and we have the intercept over here, and I'm unable to write the values over here. So let's do one thing. Let's quickly clean the board and represent the entire graph plot in a bigger and better manner. So I have redrawn the graph plot in a bigger manner so that everything is legible. So here the first line, this represents the uninhibited reaction, that is alpha is equal to 1 and apparent Michaelis constant is equal to the true Michaelis constant. And then as we increase the inhibitor concentration, okay, alpha is equal to 2 from alpha is equal to 1, you see the slope increases. From it is clear from the Lineweaver Burk equation. And here now the intercept on 1 over S axis becomes minus 1 divided by Km prime 1. And similarly, with further increase of the inhibitor concentration for alpha is equal to 3, we have even steeper slope of the double reciprocal plot, and obviously the intercept changes and it shifts towards the zero value. That means the intercept becomes less negative from higher negative value. But one thing we have to remember that all these graph plots have the same intercept on y-axis, that is 1 over v-axis, and it represents 1 over v max. And from the Lineweaver Burk plot, we have already seen that for this kind of competitive inhibition, v max remains constant. The maximum velocity doesn't change. So therefore, we can write the salient feature of this competitive inhibition, that is number 1, Km, that is Michaelis constant, increases with increasing I. So all these three graph plots have been drawn in under the consideration that apart from the alpha is equal to 1 in all other two other cases, the inhibitor concentration is being increased. So the Km increases, and number 2, Vmax, that is the maximal velocity, remains same. Vmax is constant, it does not change. And number 3, the velocity V. Can you tell me what happens to the velocity of this kinetics? Yes, so the 1 over V versus 1 over S plot gradually gets steeper, means definitely at the same substrate concentration, if I draw a straight line over here, so any arbitrary concentration of substrate, you see we are getting higher 1 over V value, so that means velocity decreases. So V decreases. So that sums up about the competitive inhibition in the form of Lineweaver Burk plot. Okay. So now I have a question to you, that first of all, what does this physically mean? Km increases. That means we need higher and higher substrate concentration to get the saturation velocity. But here we see the maximal velocity is constant, the saturation velocity is constant. So doesn't matter if we keep on increasing the inhibitor concentration, the enzyme would still reach the maximal velocity, but with higher and higher substrate concentration. So that means it would reach there, but slowly. So therefore, these following three salient features tells that how the inhibition is successful. So that means enzyme is unable to do its best because it needs higher amount of substrate concentration to reach the maximal velocity, and that makes the velocity slowing down. Okay, so can you draw the velocity versus S plot? So question for you, can you draw the V versus S plot for the competitive inhibition, considering we have different increasing I values? Okay, so this understanding, that is the how Km, Vmax and V, these three important parameters are changing, would help you to draw the correct V versus S plot with different I values. So once you are able to draw this plot successfully, then for sure you will be learning the total competitive inhibition process completely. So I will see you in the next lecture with two other different types of inhibitors or enzyme inhibition kinetics. So stay safe, and I will see you in the next lecture. Till then, goodbye.